folks, this is Dr. Mughal here again. I just want to share a very short tutorial on how to get started on Basys 3 board. So lab 2, which is right here, Introduction to Xilinx Vivado Design Environment. Remember here for this lab, the flowchart of designing a logic on a board would include these three major steps. So the first step is the design entry, which is basically creating your design, putting your combinational logic diagram into Verilog that we are going to use in a Vivado environment. Once we have that code, we are going to synthesize it, and then we're going to add constraints and then synthesize it again. And then we are going to generate a bitstream and then download it onto our board, so then we can see the logic on the board. So it's really a very simple process, and I'm just gonna do a quick demo. Also, here is the board, the Basys 3 board. So you got 16 switches right here, you got 5 push buttons, you got 4 LED displays screens here. These are the PMOD connectors. You can use them to extend the capabilities of your board. Maybe you can get an analog reading from a temperature sensors, or taking an input from a switch and then using it on some, like connecting into the Arduino or something like that. This is the power switch, on and off. This is a reset button, and there are multiple ways of connecting this board to providing an interface with your computer. We have the serial port, and we also have this micro USB cable. We are going to use micro USB cable in order to connect the board with the computer. This is the heart of the Basys 3 board, Artix 7. It's got almost 32,000 logic cells, so let's get started. I'm actually going to make a new project. Okay, looking at the pre-lab, what we're doing for lab 1 is basically trying different kind of gates: AND gate, OR gate, NOT gate, and exclusive OR gate, and basically verifying their logic using switches on the board and the LEDs. So you go to Vivado, you click on new project, you go to next. I'm going to say this is lab 2 underscore example. Make sure you start the name of the file with a letter character, and there's just make sure they're not, just avoid having spaces in there. Use underscore or even hyphens. I'm going to save it on a desktop, but I suggest you do it on desktop as well, and then make sure you copy it onto your network drive as well. Click next. RTO project, click next here again. Add sources. I'm going to add a file here, not add, but create a file here, and I'm going to name it, say, even though lab 2 requires you to verify the logic for multiple gates, but I'm only going to do it for AND gate in this tutorial. So let me just name it AND gate. Click OK. Click next. Add existing. We'll just skip that. Click next. And also just click next here. Now we have to select the chip on the board, the family that we have. So if you look at the let me go here. So if you look at the chip, it's actually Artix 7 CPG235 XC7A. So let's look up for that. I go to Vivado here again. So the family is Artix 7. It's right here. Package is the CPG236. CPG236, that's the package type right here. And the speed grade is -1. And make sure you choose the one in the middle right here. Okay. Alright. Basically this is selecting the FPGA target. Okay. Click finish. Would you like to close it? Yes. Okay. I was working on a different project, so I just closed that. So this is how you create a new project on Vivado. Okay. Now again, AND gate, we are going to have two inputs. Here you can define your inputs and outputs for your module. So I'm going to have two inputs, A and B, and I'm going to have one output, out and this is going to be my output. Okay. Similarly, if you have three inputs like A, B, and C, you mention C and then make sure it's selected as input. And then in lab 2 you will have AND gate, OR gate, exclusive OR gate. So you will list all of them and then make sure you choose them as output. For now I'm gonna just pick A, B, and out N. You click OK, and it will just make a skeleton file right here. You can double click here, and this is how it looks like. So the topology is pretty much same as it is in some other languages. You define your input. It's already have the topology ready for us. So input A, input B, and an output. And okay, so the way we would code for the AND gate is we say assign, okay, out N equals A, and this is the AND operator that we use, B. Okay, so for say for lab number 2 that you would do, you have assign, have one output, and out or A, and then for OR operator is this vertical line B. Okay, so this is just for the this was just for the explanation. We don't have, we only do it for AND gate. Okay, so my code for Verilog is pretty much ready. It's very easy to understand because it's like a textual representation. Verilog is a textual representation. It's a hardware descriptive language. So this is A ending with B. Okay, all right. I'm going to save this. Okay, and I'm going to synthesize my project. Okay, and it may take a little bit of time. Okay, so it looks like the synthesis was complete. It's now asking me to run the implementation. Let's just hold on to that. So I'm going to cancel this. Okay, now I'm going to create a constraint file. Okay, now what constraint file is, if you, and I'm sharing this with you, if you actually go to modules and then you look for the constraint file, it's right here. Okay, everything that we have on the board, everything that you see on the board has a line of control, or in other words, or location or address. This is switch not, right? Let's see if I can further zoom in. Okay, so if you notice, this is switch not. Okay, this is switch 1, this is switch 2, and similarly this is switch 15. This is push button 0. This is, yeah, so these are the push buttons, right? 0, 1, 2, and 3. All right, so we will actually use push button switches 0 as switch 0 and switch 1 as A and B, and we will use this LED as an output. Okay, so when the switches are on position, the LED will turn on, because AND gate logic is when both the inputs are high, the output is high. That's what we are aiming for, but we need to mention in our constraint file that we are going to use switch not as A and switch 1 as B and LED 0 as output end. So let's do that. Here's our constraint file. So everything that we have on the board is right here. Okay, these are the 7-segment displays, LEDs and switches. You don't have to copy everything from here. I just need 2 switches, so I'm just gonna use copy this part of the code and go to here. Okay, right click here, add sources, create constraint, next, create file, just name something, click OK, finish. and then you'll see under the constraint there, this is your constraint file that has a format of .xdc. Just copy paste here. Um, all right. I'm going to remove these hash. For some reason it just got pasted on one line, so I'm going to remove these hash. Also this right here. Okay, all right. Now I'm going to go back to my source file, which is right here under the design sources. This is my source file. I'm declaring input A, input B. This switch not is going to be A, switch not 1 is going to be B, and then LED is going to be out end. So I need to make sure, this is a case sensitive language, so I need to make sure that my variables here matches exactly with this over here. Okay, so switch not is going to be A, and similarly this needs to be replaced to A. Okay. This is going to be B, and this is going to be B as well. Okay, so it's basically within these curly braces. Now I need a LED, so I'll go back to my constant file, scroll down. Here is the LED. I'll just pick one LED because you only need one. Okay, so hash LED, this is just for commenting. So I'm going to remove these hashes, and because the output is out end, so I'm just copying it from here and make sure it just matches with this right here, replacing LED 0 with out end. Okay. Also, one of the thing in the way it works, the Verilog, the topology is such that you type module, which it automatically does, the software automatically does it for you, but you say module, you then define the name, make sure you don't have any spaces, and in the parentheses you define your inputs and outputs. So you can also write down as output wire out end, meaning you are defining out end as a wire, okay, data type, or you can say this is a register. Register could store a value like 0, 1, but at this point it's not really critical. And then semicolon, and then make sure you have semicolon, which means it ends the line. Okay. All right, I got the constraint file. Now I'm going to move on to the simulation part. What simulation part is going to do is, so we have, I want to try 4 different combinations. I know for my end I have 2 inputs, AA and BB, and output is out 1, say. So you got 4 possible combinations, 0, 0, 0, 1, 1, 0, and 1, 1. So I want to apply 0, 0 for a very small amount of time. Then I want to change the logic to 0, 1, and it stays 0, 1 for a very small amount of time, and then it goes to 1, 0, and then 1, 1. So I want to try these 4 combinations and simulate this end logic. Okay, so I go back to my I right click here under the simulation sources, sim_1, I right click here, add sources, add or create simulation sources, next, create file, okay, and then just name it. I'll just say end gate test bench file, click OK, next, okay, and I'll just press OK here. Here I go and I click on this test bench file, right click, and set this as a top, set as top. Okay. Now this is, which means, this means setting this as a top, because that means that this file is actually the driver. This is going to run the code for you. I'm going to double click on this test bench file, and I have the code right here. Okay, and I'll go ahead and explain the code here line by line. Okay, all right. What's going on here? This is register, and I'm declaring AA and BB as register. Why as a register? Because registers are capable of storing a value. Okay, so when the logic is 0 and 0, so I want the logic to stay 0 0 for a very small amount of time. We're going to give it a delay, maybe 100 nanoseconds. So because it's storing value for 100 nanoseconds, we have to declare these as registers. So I'm declaring my AA and BB as registers, and then I'm using wire data type for out1. Wire is just like a wire, you know, it would carry any signal 0 and 1 depends upon whatever is at the input, right? Okay, so and then I'm gonna say end gate. Basically I'm trying to add a module that I initially created which had the code here, okay, for the end logic, and I'm going to include that over here. And the way it works is it has to match with the name of the source file, which was right here, and then you say space u0 or u1 or u2 or whatever you want to use the identifier name, and then the brackets inputs, which are AA and BB, comma, out1, output. Okay, and what it's going to do, it's going to consider, I'm going to comment it, it's going to consider AA as A and BB as B and out1 as out. Okay, so going into the future, you'll be doing projects where you would make one module, but then you would add multiple modules to the same module, so you don't have to do the coding again and again. Okay, and because I had the AND gate module right here, I'm just adding it to my test bench file right here. Okay, and then I'm actually going to set the values for A and B 0. So initially I'm resetting it to 0. Okay, both AA and BB set to 0, and these are just variables. They could be anything. They could be A, they could be B, whatever. We are going to give a delay 100 nanoseconds. Okay, after 0 0, AA stays 0, BB goes to 1. AA stays 0, BB goes to 1, and then there's a delay of 100 nanoseconds, and then the AA goes 1, BB goes 0, and then after 100 second of delay, the logic goes, BB goes to 0 1, and AA was already 1. So basically we have all four combinations right here. Every time we begin, it's ended by saying end, and this is the end module. So here's the code ready for the for the simulation part, test bench file. I'm going to save it, right click and save it. You can also do it over here. I'm going to click and as you notice, you know, as I saved the file, the test bench file went up. Okay, and you'll see your end gate is actually added to this, right? Okay, all right. Now one thing I need to make sure is it's actually giving me this error right here, which means my AND gate doesn't match with the one right here. Now notice you're gonna have to very careful. These kind of small things can create an error, and you will have to learn in Verilog how to debug and troubleshoot. A and D, I mentioned end in caps. So here I'm going to change that to end and then save it back again. Okay, and hopefully that error is gone now. It is. Okay, I'm going to select my test bench here. I'm going to select run simulation and then select run behavior simulation. Okay, it'll take some time, there's an error right here. Let's see what that error is. Right, so I was able to remove the error, and the reason it gave me error was because any change that you make to any of these files, you have to save it and synthesize it, run synthesis again, which I just did again. So it was complete. Now I'm gonna select my test bench file and choose run simulation, select run simulation behavior, and it should take a few minutes. Okay, once the simulation is ready, this window will appear on your screen. You can maximize it if you like. You can right click and select the full view, and you will see right here for 0 to 100 nanoseconds we had the logic set to 0 0. So if I click here on this timeline, it says A0 B0, and as expected the AND gate is going to be 0. From 100 to 200 nanoseconds, we set the logic A0 and BB to 1, and you would expect the output to be 1, to be 0, because it's an AND gate. Let's see this combination right here when AA and BB both are 1, and we know for AND logic, whenever two of the inputs are high, the output is going to be high. And it stays high because we didn't change it after that, so it's going to stay high. So this is how the simulation works. Now I'm gonna move on to the implementation part because we want to see this output on our board. So I just clicked on run implementation. If the synthesis part has expired, it will, when you click on run implementation, it may just do the synthesis again. So just be patient with it, and it takes a few minutes to complete the process. So it took roughly a couple of minutes, but I got that implementation got complete, and thankfully there were no errors. The next step would be to generate the Bitstream. So remember I was showing you that flowchart at the beginning. We did create the schematic first. We did the design check entry, basically putting our design in there. We did the synthesis. First we selected our FPGA board device, we added the constraint, we did the synthesis, and we did the functional simulation then. Now we are into the implementation part, so we're just gonna go generate a Bitstream which will be downloaded to the board, and then we should be able to verify the logic on the board. So I'll go back here, click generate Bitstream, and then over here on the top right part of the screen, you should be able to see the status, what's going on. Again, you know, it might take a couple of minutes to generate a bit file. All right, so the Bitstream, stream has been generated, and you'll see this window pop up on your screen. Open implement design. Well, we can move on to the open hardware manager. You click OK. This is about the time you want to plug in your board to your machine. Make sure the board is on. Once you go under the hardware manager, you'll see open target, and it should automatically detect, which it did for me. I'm just gonna click on this thing. Okay, and I'm gonna click on program device now, and I'm gonna choose this XC7A350 because that is what we have on our board. It will by default automatically select the Bitstream file for you. You click program here, and your board has been programmed. So now that we have the bit file loaded onto the chip on the board, you're going to verify the logic. So this being A and B both set to 1, it's actually, if you notice, the LED is on, and that's what the logic is for the AND gate. When both the inputs are high, the output is high. Any of the inputs goes 0, the output also goes 0. So this is 0 0 right now, and this is, say, 1. Okay, all right. With this I'm going to finish this tutorial, and I'll see you guys in the lab.